Okay guys, so imagine we had an energy source that was near limitless, efficient beyond anything we've ever seen before, and environmentally friendly. Well, to me that sounds like a dream, right? But that's actually what I'm going to be talking to you guys about today, and how Mufu Energy, the company that I recently started with Ben, is going to make that a reality. And imagine creating that with something as simple as a glass of water in your backyard. Now I'm pushing it a little, right? Now it's a little impossible, but hopefully I'll walk you through, and by the end you guys will be convinced that we have a legitimate hypothesis that we're going to validate and hopefully make a change in the world. So first, let's talk a little bit about the energy problem, not just how we're going to solve it. So right now, I think you guys know the majority of our energy is non-renewable and is currently degrading our planet. So it's actually 85%. And up to now, it just made sense, right? It's cheaper, it's more portable, it's easier to get. And oftentimes, people don't have a choice, right? 3 billion people are still forced to use energy sources like coal, animal manure, anything they can do to, heat their house. But I think you guys know that if we continue on this path, we're going to end up, it's not going to be a matter of losing out because our non-renewable energy resource is going to run out. It's going to be the fact that our Earth is on fire and we can't really live here anymore, right? So how are we targeting this? So I started, as I mentioned, Mufu Energy. So we're aiming for limitless, efficient green power. So how are we going to do this? Ironically enough, with something many people coin the future of energy, fusion energy. The way fusion energy works is it commonly takes two isotopes. So like isotopes of hydrogen could be like Deuterium and Tritium. And they're going to combine together, and they're going to release helium, a neutron, and a whole lot of energy. So the current problems with this is that it's really hot, right? So fusion energy is the type of stuff that powers stars. So if we want to simulate, 120 million degrees Celsius in an environment on Earth and generate an energy surplus, it's going to be a little hard. So, our company is a little cooler than that. What we're doing is cold fusion. So cold fusion basically is doing this exact same reaction, but at room temperature. So there's been a lot of, I don't know if you guys know the term like FUD, there's been a lot of fear, uncertainty around the term cold fusion, research in cold fusion. And the reason why is because, well, most of the claims have been illegitimate. A lot of people promised the world and literally they just had like a badly written paper. But there's one thing that stuck in the last 100 years, Muoncatalyzed fusion. Muoncatalyzed fusion is, I'll explain it to you guys with this video, or can I just, oops, got you guys a peek of Einstein. Anyways, I'll just explain it. So basically, muon-catalyzed fusion is using a muon, which is like, you can think of it as a particle that's like an electron, except like 200 times heavier. It's using a muon to stimulate, catalyze this reaction between two hydrogen isotopes at room temperature. And so we got to thinking, well, the current problem with this is, it's pretty legitimate, right? And research has backed it up, but it actually generates an energy net negative. So a muon has a lifetime of like 2.2 microseconds, okay? And in that time, it can generate 100 reactions, but the energy it gets from those 100 reactions is actually less than the energy it takes to create the muon. So we were thinking, how can we, make this poor little muon live a little longer, right? We want to create some energy positive, make everybody happy. So actually, Einstein answers this question really well with his theory of special relativity. And there's a concept within that called time dilation. And it basically says that the closer you are to the speed of light, the slower time moves for you. So a common way of explaining this is like the twin paradox, right? So I have a twin and I go on a rocket ship to Mars, I come back, I go near the speed of light. And when I come back, I'm actually going to be younger than my twin because I was moving at way faster speeds. So from the concept of time dilation, we actually get this formula. And warning, it's going to get a little boring. We have to do a little math. So from this formula and actually a few pieces of information we already know, we're able to figure out how fast the muon needs to go in order to generate an energy positive. So to see if it's actually viable, right? So we know that we know the time that it takes for a muon to decay is 2.2 microseconds. We know c is just the speed of light, and we want to solve for v. So the one thing that we have left is dilated time, or the t with the apostrophe. So we can think of time in the equation like rate of reactions equals number of reactions over time, okay? And we actually know that a muon is able to do 100 reactions in 2.2 microseconds. So that gives us a rate of 45 reactions per microsecond. And then representing that in another way, we're gonna isolate for time now, keep the rate that we just calculated, and we're just gonna leave number of reactions as a variable, and we're gonna sub it in later. So time is gonna be equal to number of reactions over rate, based on the above formula, and then that's actually gonna equal the other side of the time dilation equation. And from there, we can isolate. So this is just a lot of boring math. From here, we go to the final equation, and we know the number of reactions based on research done that it takes for a muon catalyzed fusion to generate a net positive is 300, right? So we're gonna sub in 300 into our equation, and we're gonna get 0.94 C, which means we need to go 94% the speed of light in order to generate an energy positive. And I was thinking, when I saw this, I'm like, shoot, that means we're like screwed. I got excited, I did all the math, and Ben helped me, and now we can't really do anything. But what I didn't know is 94% the speed of light apparently isn't that much. We have things like the Large Hadron Collider, which are able to go 99.99999, it goes on for a while, % the speed of light, right? But I mean, if you look at this is like 27 kilometers in radius. And I promised you guys it would fit in your backyard, so I don't know if that's gonna work out. But fortunately, there's other alternatives we can use. So just a brief explanation of how this would actually look. First, we start with the muon generator. So the muon generator would work is you're just gonna, this is already solidified science, you just like collide a bunch of particles, usually protons. They're gonna form pions, they're called, and then they're gonna instantly decay into muons. The muons are gonna get sent into here, and here's the accelerator. It's a vacuum. So what we were thinking of using is an FFAG accelerator. Not really important for now. But anyways, we're gonna speed it up near the speed of light at like 94, 95%. And once it reaches that speed, the core, which is deuterium and tritium stored in either gas or plasma, is gonna start seeping in to where the muons are. And even though the muons are going at such a fast speed, the energy of charge, of attraction between the negatively charged muons and the positively charged deuterium and tritium is actually stronger than that speed, and they're still gonna combine and make fusion. So there are a few things that we need to improve on to make this technology viable in the next few years. So the first one is we need more efficient, cheaper, portable muon generators and particle accelerators. So the great thing that I think makes this viable is the fact that once something goes from research to commercialization, the price will drop magnitudes of order. So a good example of this is with coding a human genome, right? So Illumina is claiming they're gonna do it for $100, but once upon a time it cost 2.7 billion. So that's a decrease in factor of price of 270 million. And actually, so the Large Hadron Collider, the thing I showed you before, it costs like 6 billion to build, costs like $1 billion every year to operate, billions more for every experiment. Just last year, they were able to create a particle accelerator that only cost $93 million, and instead of being 27 kilometers, it's 27 meters. And now they're set on making it 1 meter. That's what they're working on right now. So that makes me pretty optimistic, 5, 10 years, it's fully feasible. The second thing that we really need to work on is generating tritium sustainably. So currently, tritium, one of the isotopes I've mentioned, is generated using lithium. So this is actually a lithium mine here. And the problem with that is lithium is probably going to run out. If we were to power all of the world with deuterium and tritium, it's probably going to run out in like 100, 200 years. So we need to think of another way to manufacture tritium. Deuterium, on the other hand, is great because we can just find it in our seas, oceans. It can last us billions and billions of years. And we can actually do deuterium to deuterium fusion, but the problem with this is it's substantially less effective. So actually, how I said for 2.2 seconds that a muon exists, it's able to catalyze 100 reactions for deuterium tritium. For deuterium, that number goes to 12. So it's like 8 times less. So we're going to need substantial improvements in technology to maybe make the muons at a cheaper rate, such that this would be feasible. But if it is, that's billions of years of energy. The main point here is I think fusion is going to be a field that has a lot of impact, and I'm confident that MUFU energy is going to be at the core of that. And if this were actually feasible, cold fusion could make the energy distribution decentralized. So that means you could literally make it in your backyard. So this could reach everyone and anyone. If you're on the mountains, wherever, or if you're in the city, it can power cars, it can power houses, it would power everything in a decentralized way. The point is, the field's going to be explosive, but not literally, because a big misconception is fusion actually doesn't have any negative environmental impact. So you guys might be thinking of fission like meltdowns and things like that, but fusion actually doesn't have any negative environmental impact. So the point of the story is fusion's going to be huge, and I'm super excited to have a role in it and test out my hypothesis with Ben. So thank you guys for listening.